This is 2.1 functions. We're going to talk a little bit about interval notation first. So we have inequalities up here, and I'm going to show you how these will be written in interval notation. We have the first one says x is greater than or equal to c, and x is less than or equal to d. The way we would write that in interval notation is using what's called a closed bracket. C on the left, D on the right, and the closed bracket means it includes those endpoints. Then you'll see that the next one, we have it closed on one side. It says x is greater than or equal to c, but open on the other side. The open is the open parenthesis, looks like that. So it says x is strictly less than d. That means it does not include d. And then we have open on the left, closed on the right. And then this one is open on the left and right, so that says x is between c and d. And then we have here x greater than or equal to c. What we'll use is a closed bracket on the left for c.
Good morning, Eldorado and Vista High. This is your tutor.
Okay, so the closed bracket on the left-hand side says x is greater than or equal to c, and then it's going to go up to infinity. And we always have an open bracket at infinity because infinity is not a specific number, so it is open-ended. You give me a number that's really big, I can give you one that's just a little bit bigger, so keep going. So we leave an open bracket there. X greater than c would be open on the left at c and going up to infinity, and then open. X less than or equal to d would be everything from negative infinity on the left, if you picture negative infinity on the left of the number line, up to and including d. So any values from negative infinity up to d, that's x is less than or equal to d. So let's think of it as values less than or equal to a specific number d. Like d could be 10, so 9 would work. Negative 2 would work. Negative 3,142.3 would work. X less than d, we have negative infinity up to, but not including d. And all reals we can represent in interval notation by going from negative infinity to infinity. All right, let's look at graphs. Graphing intervals on a number line, just so we can get a picture of what some of these intervals look like. From negative 2 to 9, looks like this. We have an open circle at negative 2, closed circle at 9, and we're shading everything in between. If we take negative infinity up to 3, but not including 3, we have an arrow to represent we just keep going to the left, but do not include 3. And then 2 to 5 would be closed circles on each end, shading in between. So there's 2 to 5. All right. We're going to solve the inequality and express our answers in interval notation. So here's how we go about doing this. We're going to go ahead and factor this. Just treat it as if it were a quadratic equation. So we'll go ahead and factor it. And we have x minus 1, factors of 3 that add to equal negative 4, and x minus 3. And we're going to set that equal to 0 and just use those as what we call critical points. So x minus 1, x minus 3, that would mean x minus 1 would equal 0, or x minus 3 equals 0 by the zero product property. So x equals 1 or x equals 3, we call those the critical points in calculus. And those are the boundary points that we're going to break up our number line into. So we take our number line, here is 0 in the middle, here's 1, 2, 3, let's go a little bit past 3 to 4. We've got a couple of critical points here at 0, or at 1, and at 3. So you can picture this as 3 separate segments. We've got segment 1 from here to here, segment 2, oh, we didn't go far enough here, all the way up to our critical point. Let's try that again. So we have segment 1 going from negative infinity up to my first critical point, segment 2, from critical point to critical point, and segment 3 from the second critical point up to positive infinity. So 3 different regions we need to test, and we're going to figure out which region is the correct region. So what we do is we pick a test point. So pick a test point somewhere between negative infinity and 1. Say and we don't want to pick 1, it's not included, but say we pick 0. That's an easy one to try. So we could maybe try 0 in the inequality and see if we get a true or a false statement. If I plug 0 in there, 0 squared minus 4 times 0 is 0, plus 3, I get 3 is less than 0 when I try 0 in here. So I plug in 0, I get a false statement. 3 is less than 0, that's a false statement. So this region is out of the mix. I can take this out of the mix. That one is not a region with values that work in the inequality. Good test point for the second region would be to try 2. That's the whole number in there. If I try 2 in my inequality, I get 2 squared is 4, minus 2 times 4 is 8. So 4 minus 8 is negative 4, plus 3 is negative 1. Negative 1 is less than 0. That is a true statement. So this region is shaded, meaning any values between 1 and 3, not including 1 and 3, will work in that inequality. And then the last region here, we could try a test point of, say, 4. I'm just choosing the easiest test point I see in that region, a whole number preferably, something that's not too large. I'm going to plug in 4, 16 minus 16 is 0, plus 3 is 3, 3 is not less than 0, that is false. So that is out of the mix. So we have a solution set between 1 and 3, and if I do that in interval notation, I would say the solution is the set of all x between 1 and 3. We can do that by saying set of all x such that x is an element of, that's symbol is an element of the interval from 1 to 3. That's our solution set for that inequality. All right. Moving on to the idea of domains. That's interval notation, writing things in interval notation to replace inequalities. We use them interchangeably in calculus. A domain, let's talk about domain of a function f. Here's the definition of domain. It's all reals, there's the symbol for reals, all reals such that the machine produces a real output. So the domain of f is the set of all real numbers such that when you put that number into the function, we sometimes call that a function machine, there's an output for each given input, but the output is a real number. Okay, so a couple rules here is no division by 0. That's something we've seen before. You've seen that now, Algebra 2. No division by 0. So that's something to watch out for when it comes to domain. There actually, as we look through the pre-calculus course, we're going to be adding one more restriction dealing with logarithmic functions. But what you've seen so far is that you cannot have a rational function with a 0 in the denominator, so that helps us define domain. I'll show you what I mean in a minute. And no even roots of a negative number. So we're not just talking about square roots, we're talking about fourth roots, sixth roots, and so forth. So these are the two restrictions you've seen up to this point. Like I said, we'll add another one dealing with logarithms. If you guys with logarithms, you cannot have an argument or input that is 0 or negative. So it's strictly all values greater than 0. We'll add that in when we get to our unit on logarithms. So here we go. Number 3, we're going to be asked, what is the domain of each function? So on number 3, we have a domain restriction that fits one of these two categories, and that is we cannot have 0 in the denominator. So we set x minus 1 equal to 0, and we solve. So x equals 1. You can see that visually. And so when x equals 1, the bottom is 0. So if we were to determine the domain of this function, it would be in interval notation from negative infinity to 1, and this is called a union. Union means or, from 1 to infinity. And so on the number line, if I were to draw a picture of that, it's all values except for the value 1 on the number line. So if this were 1 right here, it's everything on the number line but that 1. Okay. So that's the domain of that function. It's all x values such that x is an element of this set from negative infinity to 1 union 1 to infinity. Number 4, it says b of f equals square root of f plus 2. So we know that the second restriction applies here. We cannot have an even root that is negative. So that tells me f plus 2 must be greater than or equal to 0. It's okay if it's 0, but it must be 0 or positive. It cannot be a negative number. Solve this for f. I get f is greater than or equal to negative 2. If I write that in interval notation, it's a set of all x such that x is an element of the following closed half open interval, I should call it. It goes from negative 2 on the left to infinity on the right. If I were to draw a picture of it on the number line, here's negative 2 right here, here's 0 here. It's a closed circle and goes to the right. All right, number 5. We know, this fits with the restriction number 1, that the bottom cannot be 0, so we set k squared minus 9 equal to 0. If I factor, I get k plus 3, k minus 3 equals 0. We know by the zero product property, k equals negative 3 or k equals 3. And so this one, using interval notation, would be, oh, there's one more thing here. We also see that on the top, we have a square root function. There are going to be some restrictions on that as well. So we need to set that up. I'll do that with a different color. So we first established that the bottom cannot be 0. Also, we can not have any even roots of a negative number. So I'm going to set k minus 2 greater than or equal to 0. That gives me k is greater than or equal to 2. And so we have to somehow combine these two together. If I were just looking at the top one here, k equals negative 3 or k equals 3 are the restrictions, I would have everything on the number line shaded except for open circles at negative 3 and 3. But this is also saying that 2, k must be greater than or equal to 2. So we're not going to use any values to the left of 2. So when I combine these two together on the number line, here's what it looks like. Draw my number line. I have value here at negative 3 with an open circle there. It's messing up on me here. Try this again. So I have negative 3 here with an open circle, and then I also would be shading left and right of that. I also have an open circle over at 3. Circle there. But I'm also restricting it a little bit more in that I'm saying that it must be greater than 2. So I'm shading all this stuff to the right of 2, but not that open circle. So how do I reflect that in interval notation? It would look like this. We go from, on the left, 2 to open 3, union, open 3 to infinity. And that would represent all the values of k that are in the domain of this function that combines a square root and a rational function. All right. It says compute, number 6 says compute and simplify the difference quotient. I should probably write down the difference quotient or look at it here. Difference quotient is an equation. It's a quotient. You can see this is why it's called the difference quotient. We have on top a difference, and because it's a fraction, it's a quotient, division problem. So we have f of x plus h minus f of x over h. We use this in the definition for a derivative in calculus. Once we apply the limit to this, it will give us the definition of the derivative in calculus. You should recognize this as something very similar to m equals y2 minus y1 over x2 minus x1 And you can see the y2 minus y1 on the top. X2 minus x1 simplifies to h. It's of the same form as the slope of a line. So we're going to compute and simplify the difference quotient. We've got some algebra to do on these down here. We're going to basically plug in. Okay, I had to recalibrate the board here, but what you should know, this is called the difference quotient. Now you're going to be asked to simplify the difference quotient for a couple different functions. Each function has a different difference quotient. This is a big idea in calculus. We actually use the difference quotient to define, along with the limit, to define the derivative, which is a first semester Calculus 1 big idea, a tool that we use to analyze functions. So you may recognize this. It looks kind of like your slope formula, which is what I was saying. It's m equals y2 minus y1. You can see that on the top, over x2 minus x1. The h actually represents a very small or minuscule difference between x2 and x1, and we call that h. So we're going to go ahead and simplify the difference quotient, apply this function. What we're going to do then is take the x plus h and plug it in everywhere we see x in here. So the first term, f of x plus h, will look like this. Negative 4, block parentheses here, times x plus h plus 1. And so this first term represents just the f of x plus h part. And then I have minus f of x. F of x is exactly negative 4x plus 1. Substitute that in, all over h. Then I simply simplify it, distribute here, combine like terms, negative 4x minus 4h plus 1, careful with the signs here, plus 4x minus 1, all over h. And missing an h here, negative 4x plus, there it is. Here it should be a minus 4h. What you should notice on these, what kind of clued me in is the terms without the h's in it should cancel out on these, most of the ones that I give you. If that's not happening, you may have made a mistake in your algebra, as I did here, or a copying error. So we have negative 4h over h, and then you should find that on these difference quotients, as you simplify them, the h from the bottom gets simplified out on the ones that we're doing. So there it is. Negative 4 is the simplified difference quotient. And it has significance in calculus. You'll have to come back. You have to go on to calculus to hear more about that. I may allude to some of that as we get towards later on in the year. We're going to take a little more difficult function here. F of x equals x to the 4th. Apply the same formula to it. So we're going to plug in x plus h, 4x. This is the first term. That's the f of x plus h term from the difference quotient. There it is, right there. And then minus f of x, which is just x to the 4th. That's this guy right here. And then that's all over h. Now, expanding out a binomial like x plus h to the 4th, you could do it by multiplying x plus h times x plus h times x plus h times x plus h. Or you can use the binomial theorem. The coefficients of the binomial theorem we get from Pascal's triangle. That's probably the way you've seen it. If we're only going down to the 5th row or to the 4th degree row, we only have to build Pascal's triangle, 5 rows of Pascal's triangle, so that's not too bad. So we have a 1 on the outside here, 2 in the middle. Remember, we're adding the 1 and the 1, and 1, and then we have 1, 3, 3, 1. And finally, the row that we need, 1, 4, 6, 4, 1. It starts at the 0th power binomial. This is first, second, third, fourth. So we're going to use the 4th row. As a matter of fact, this 4th row right here gives me the coefficients of the expanded out binomial x plus h to the 4th. So it looks like this. We have 1, 4. I'll leave a little bit of room because I have some variables I got to fit in here. And then off the end, I'm going to have minus the x to the 4th. So right here, starting at number 1, we start with x to the 4th, and then we go down x to the 3rd, x to the 2nd, x to the 1st, and then x to the 0 would be 1. And with the h, it's h to the 0, which would be 1, and then h to the 1st, h to the 2nd, h to the 3rd, and h to the 4th. And in between we have all plus signs because it's x plus h to the 4th. And then I have, that's all the f of x plus h term. That's this part right here. And then I have minus x to the 4th. That's the f of x part, all over h. So what you should notice, if you've done this correctly, is that the terms without the h's on the top should cancel. They do in this case, at least for the ones I'm going to give you, they will. And I have 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the 4th all over h. Then, as you can see, there's an h in each term on the top. You can factor out an h from the top. Left with 4x to the 3rd plus 6x squared h plus 4xh squared plus h to the 3rd. That's what I get when I factor out an h. That h then cancels with the h on the bottom, leaving me the simplified difference quotient 4x cubed plus 6x squared h plus 4x h squared plus h to the 3rd. Box it. That's your simplified difference quotient.